lab works on developing novel optical microscopy techniques for various imaging applications. The work in our lab is very comprehensive. That involves understanding how light interacts with objects, building novel imaging instruments, performing image reconstruction, and post-processing. We work with material scientists, biologists, and doctors to promote our imaging techniques. Let me show you the optical microscopes in our lab. Optical microscopy techniques have been widely applied to imaging biological structures and disease diagnosis. Our lab is developing optical diffraction tomography techniques for high-resolution 3D cell imaging that can be potentially used by pathologists for cancer diagnosis, such as glioblastoma. ODT is a label-free imaging technique that does not require complicated fluorescence staining. Here we show a demonstration of cell tomography imaging in a commercial ODT system. Before measuring cells, say erythrocytes, we first drop the cell culture onto a glass slide, then we cover it and mount the slide in the ODT system. After adjusting the position, we are ready to image the cells. Now we select one particular erythrocyte. By performing different angle projection measurements similar to X-ray CT, and with an inverse scattering model, we obtain the 3D image of the erythrocyte. The color represents the 3D refractive index distribution in the cell, which is related to the subcellular structure, protein concentration, and shape. At CUHK, we are working on transforming ODT into a useful biomedical imaging tool by collaborating with doctors and pathologists. According to WHO, in 2016, close to 500,000 people died from malaria infection, mostly in underdeveloped areas such as Sub-Saharan Africa and South Asia. However, medical diagnosing devices are not widely available in those areas because the medical devices are too expensive and difficult to set up. To address those issues, we are developing portable quantitative phase microscopes. Although at a very low cost, they can still achieve a very high imaging performance that can meet certain diagnosing purposes, such as malaria and other blood-borne diseases. The system is easy to set up and the sample preparation is simple. After preparation, we mount the sample in the system. A home-built real-time processing software is developed to visualize and analyze the images. We also plan to implement the real-time software into mobile platforms, so that the imaging data, such as red blood cell morphology, mechanics, and so on, can be easily shared with experts for timely diagnosing diseases of patients in remote areas. Such devices can be also used for monitoring the daily health status of individuals and families. Always be curious about new things and open to different views. This is what drives me to talk with different people and learn from them.